Hi, I'm Campolattaro. Julius and I are going to demonstrate the functionality of our end product and discuss some of the design decisions we made along the way. The product consists of a pipeline which is separated into 3 distinct stages which could be built and tested separately. We have the hardware input stage, the digital processing stage on the Arduino, and the hardware output stage.
Hello, my name is Julius and I'm here to talk about the hardware input methods for our project. The first stage of our hardware input method is the microphone biasing circuit, which is designed to follow the same schematic shown on the screen here. This is the constructed microphone biasing circuit on the breadboard. The second stage of our hardware input method is our bandpass filter. Initially, we thought that a first-order bandpass filter might be a possible solution. However, we decided this is not optimal because the attenuation at frequencies other than 1 kHz was not high enough. In order to obtain a higher attenuation at frequencies other than 1 kHz, we decided to use a fourth-order bandpass filter as shown in the schematic here. The theoretical Bode plot is also shown, and you can see that it has a much higher attenuation at values other than 1 kHz. This schematic worked effectively for us. However, we realized that we could obtain a higher range of features by changing the resistor and capacitor values. One of the features we figured we could add to our bandpass filter was to have the filter also be capable of not only filtering out frequencies, but also amplifying signals. So our solution was to use the 20 times gain filter, as shown in the schematic here. This filter worked reasonably well for filtering purposes. However, unfortunately, 20 times gain did not seem to be enough, as the waveform software and the Arduino software had issues with picking up the signals and analyzing them. In order to remedy the issue of the gain not being high enough, we decided to use a 100 times gain filter instead of a 20 times gain filter. This 100 times gain filter was constructed according to the schematic shown here. This 100 times gain filter allowed us to pick up signals from greater than 3 feet away while still having the output signals from the filter be legible by both the Arduino and the waveform software. The constructed version of our 100 times gain fourth order bandpass filter is shown on the breadboard here. We performed an AC frequency sweep on the filter in order to test for functionality using the waveform software. It should be noted that this first test was performed by directly wiring AC signals into the filter. In other words, we had no interaction with the microphone in this test. We performed a second, similar test on the filter in which the microphone was taken into account. The signal output from the analog discovery device was routed into a piezo transducer for this test, instead of directly into the filter. The microphone was then set up to pick up signals from the piezo transducer, then feed the signals into the filter. Doing so allowed us to generate the Bode plot shown here. It is noticeable that there is a sudden spike in the Bode plot at around 2.7 kHz. This, however, was due to resonance in the piezo transducer and not due to the filter itself.
The software stage of our pipeline takes the analog input from the first stage, digitizes it, encapsulates it in a nice format to read, uses that to find the phase and then the direction, and outputs that direction in a format that the hardware output stage can use. The software section of our pipeline is an Arduino program which we've separated into several distinct components which we can test separately. The sample array header provides a set of operations that can be applied to arrays of samples. A sample is a single data point that represents the magnitude of the input signal. We chose a small data type for the samples because the Arduino has a very limited memory capacity. Some examples of functionality provided by sample array include average array, which finds the average value of the samples in an array, normalize array, which subtracts that average from every data point to center the data on 0, and peak index, which finds the location of the largest sample in the entire array. A buffer is a data structure created to contain 2 arrays of samples, representing the left and the right microphones. The buffer class provides a lot of useful functionality. For example, the fill method fills both sample arrays with data points and records the time it took to record them. The delay by peaks method finds the delay between the 2 input signals by comparing the location of their peak samples. The LED display header is a piece of software written by Julius for interfacing with a set of LEDs to display the angle we found. The main file of our Arduino program pulls all this functionality together into a final product. In the setup, we set the Arduino's prescale divider so that it can run at the fastest possible speed, and then we initialize all the inputs and outputs. Each loop, we initialize the microphone pair, which fills its buffer. Then we use its functionality to find the current direction of the audio source. We make sure that that direction is a valid value, and then we include it in a rolling average so that our values are smoother and easier to view. Finally, we use our output to display the new value for the user.
The hardware output method used in our design is the simple LED board shown here. This LED board is controlled by a finite state machine in the Arduino's code, which Jackson mentioned earlier. And now for a demonstration of our design. Fair warning, if you have sensitive hearing or you are wearing headphones, it may be a good idea to temporarily mute your volume. So for the first demonstration, I'm going to use a 1 kHz tone, and I'm going to revolve the generator of the signal around the pair of microphones slowly to show that the device is working. And now, to demonstrate that this device is selective, I'm going to also do the same with a 2 kHz tone. As you can see, it didn't pick up the 2 kHz tone and track it the same way it did with the 1 kHz tone, which shows that this device is not only capable of tracking a 1 kHz tone, but it's also capable of successfully filtering out for other frequencies that are not at 1 kHz. Thank you for watching, and I hope you enjoyed our video.